Last week we talked about Archimedes method. It is a method of tying in sequence series to area under a curve. This is the shape. If you were to draw this, what's the width from here to here? 1 to 3. 2, right? What's the height here? If you put a 1 in here, it's going to be up to the 8, right? And you put in a 3, it's going to be up to the, what, 14? So this is going to be 16, and then this is going to be 6 times 2 is 12. Half of that is 6. I think the area should be equal to 22. That's what it should be. So let's see. You're going to find the area from 0 to 3, area from 0 to 1, and we'll have, let's do 0 to 3 first. We have n rectangles. And what's the width? The width of each one. So if we go from 0 to 3, we're going to say it's 3 minus 0 over n, or 3 over n. The height for the right edge is the width times I plugged into the formula. So the width times I is just going to be 3I over n. So the area is the limit n approaches infinity of the sum. I goes from 1 to n, right? And we do the height, which is 3 times 3. Let's just do 9i, if you don't mind. 9i over n plus 5 times width, 3 over n. So this is going to be the limit n approaches infinity of the sum. I goes from 1 to n. Careful here. This is going to be 3 times 9 is 27i over n, plus the sum as I goes from 1 to n of 15 over n. How you doing? Just multiplying those out. Emma, is that okay? Who asked for this one? Oh, you did. Emma, so what do I need to clarify? All right, so the question was, what happens with the 5? So let's think of it this way. This is the same as 9i over n plus 5 times 3 over n. Do you agree with that? So see how I did 9i over n times 3 over n? This should be a square. Kurt, you're going to catch that, didn't you? No? Oh, this should be n squared. The number one error, I just made it. And then the other is 5 times 3 over n is 15 over n. And I just split these into 2. Yeah?
So why is the height equation 3 times 3i over n and not just 3 times I?
Over n.
Or is it not just 3 times I plus 5?
Good question. It's the toughest part here. Is this still rolling? Yeah. So let's do it. Let's go nice and big here. So is this the 3i, is a 3x plus 5? Okay. So this is 5. And we're going from 0, what was that, to 3? Okay. So we're dividing this into strips. And we're going to use the right edge. And the reason we like that is because we start with this x. We call this x sub I, the location of the x value. Well, how far apart, Kurt, are each one of these? They're each 3 over n, right? Because this is 3 over n location, 6 over n location, and so on. Is that part all right? Okay. So what we can do with that is we can say this is take out a 3 over n and just call this rectangle 1, 2, 3, 4, 5, all the way to to that n. Now, but it's times 3 over n. So each xi, this can be replaced with I, and then we multiply by 3 over n. So what we came up with is, let's say this f of x is 3x plus 5. Then what happens is we take this and shove it into the function to make it, for the height, or the y part, height. The height is going to be this width times I, or 3 times 3I over n. 3I over n. Is that part okay? That's the hardest conceptual part of this whole proof. But if you just remember, it's f of the width times I. Just find the width, multiply by I, and just put it into the function. You'll be fine. It'll go great. Okay, so did you see my little error there that I corrected? This n times n gives you n squared. All right, am I good so far? Yeah. Okay. So now it's just a matter of evaluating it. So we take the limit n approaches infinity of the sum. I goes from 1 to n. We're going to put the I here and pull out the 27 over n squared. Plus I equal 1 to n. We're going to pull out the 15 over n and leave 1 out here. This is something, and this is something. So let's see what it is. Limit as n approaches infinity, 27 over n squared. What is the sum as I goes from 1 to n of I? Yep, and I'll give you those. But it's going to be whenever you do 1 plus 2 plus 3 plus ... all the way to n, you just take whatever the last one is, n times n plus 1 over 2. And that can be replaced for 1 plus 2 plus 3. That's nice to know. So we can replace this with n times n plus 1 all over 2. Now if I have 1 plus 1 plus 1 n times, what can I replace this summation with? N. And here's where you get, Emma, this is your question, where that 15 comes from. So this is going to be the limit 27n squared over 2n squared. What's 27n squared over 2n squared? 27 over 2. Plus the n's canceling out will be 15. Where did this where did 27n over 2n squared go? 27n times 1 over 2n squared. What happened to that? Goes to what? If your limit goes to infinity, goes to 0. So we only care about the greatest exponent of n. So I circled the coefficients and the greatest exponent of n. 27n squared over 2n squared is 27 over 2. 15 times n over n is just 15. So we're going to hold on to that. And now you're going to go from 0 to 1. Go for it. The second half, we have n rectangles, width 1 over n, height 3i over n. You just take the width times I and plug it into the formula. Can't space that here. There we go. You just put that right in for x. So there's where you get 3x plus 5, 3i over n plus 5. Then when we do the limit as n goes to infinity, you get 3i over n times 1 over n is 3 over n squared times I. I just pulled the constants out. And you'll have 5 over n. Pull that constant out, leaving the 1 over n. If that step was too abrupt, Let's do the in-between one. Area equals limit n approaches infinity of the sum as I goes from 1 to n, 3I over n squared, plus the sum as I goes from 1 to n of 5 over n. And then I just, whatever the constants were, I pulled out. 3 gets pulled out, n squared gets pulled out. 5 gets pulled out, 1 over n gets pulled out. So now what we have to do is to evaluate this, but we did this before, so this is no biggie. Limit n approaches infinity, 3 over n squared. What do you replace this with? N times n plus 1. I have them up on the board too. Over 2. Plus 5 over n. What is the sum when you go 1 plus 1 plus 1 n times? That'll just be n. So this one, when I highlight the greatest exponent of n in each part, 3n squared over 2n squared, what's that going to be? Yeah, that's just going to be 3n squared over 2n squared, 3 halves, and 5, which will be 3 halves plus 5. Doing all right? So when we get to the top here, 0 to 3 was 27 halves plus 15. 0 to 1 was 3 halves plus 5. What do you do with 0 to 1 and 0 to 3? You subtract them. So 27 halves minus 3 halves is 24 halves, and 15 minus 5 is 10. What's 24 halves? 12 plus 10 is 22, isn't it? So we got it. That one should be easy, but I don't think it is. I think it's tricky with that little constant. Nice job.